definition right now, right? Oh, I'm sorry, it's not even continuity. Never mind. Forgot to say. I want to evaluate this limit. So we're allowed now to just say that since this is a continuous function in here, the limit of it is x goes to 0, just plugging in 0. We're not going to justify all these plugins we've been doing, right? It's all based on continuity. We did it before without any justification. Since this function is continuous, what does it mean to be continuous? That the limit as x approaches a value for this function is the same as the function at that value, right? Is the same as plugging in. That's what the definition of continuity is saying. So now you're allowed to say, well, since this function is continuous, and I'm composing it inside another continuous function, right? This is the x to the 8th minus 3x6 minus 1 is being put inside the x to the 40th function, right? You're composing them together in a sense. Since I have a continuous function composed into a continuous function, it remains continuous. And so the limit, as x approaches 0 for this thing, must be just plugging in 0. That's what it's trying to say. It's justifying all the plugins we did, right? So too for all of them. 21. Find the intervals of continuity. X to the 5th plus 6x plus 17 over x squared minus 9. All right, that's our function. Where is this thing continuous? Well, the top is continuous everywhere. It's a polynomial. The bottom is continuous everywhere. It's a polynomial. And I'm taking their ratio. So they're going to be continuous everywhere except for the number is 0. Right. Which happens where?
Plus and minus.
Right. X cannot be 3 or negative 3. That's where this thing will fail to be continuous. Right? So therefore you'd write your answer, the interval of continuity that it does possess, since it's an interval of continuity, you want to write it in interval notation, negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. That's its interval of continuity, or intervals of continuity, right? It's not one single interval. Again, based on the fact that it is a ratio of continuous functions. Continuous everywhere except where the bottom might be 0.
Wait, so
We're not looking at a point, we're looking at the entire thing.
That's right. This is intervals of continuity. That's right. That's why you want to know about that information there. Where all these types of functions you usually deal with, where are they continuous? What's the broadest range of their continuity? That's what you want to know. Yeah.
so right there you're saying that everything is continuous except for that? That's why you wrote that?
That's these 2 points are where it fails.
Yeah.
Right. Fails to be continuous. It is discontinuous there. It fails continuity there. And we know that simply because it makes the denominator 0. That's all we're looking at. Otherwise, let's say I had multiplied them together. Let's say f of x was the product of these two, x squared minus 9 and x to the 5th plus 6x plus 17. What is the interval of continuity for this, the product of the two? Everywhere. Because they're both polynomials. This is continuous everywhere, this is continuous everywhere, and I'm taking their product. So the result is the same, continuity everywhere. The only reason there's an exception here is because of the division process.
So when something happens like that, you're just going to say except for here, and you're going to write that there? Like
Yeah.
the intervals?
Yeah, you want the interval. This is your final
Okay.
answer. You want to tell them where it is continuous. That's what you want them to know.
Oh.
The more important thing is to realize when you see combinations of functions, additions, subtractions, products, compositions, if it and its other, right? If this one and this one are both continuous and you're producting them together, then they're going to maintain that continuity. The only problem is when you divide them, you have to worry about the bottom being 0, right? If there's a plus between here, the answer would be continuous everywhere. If there's a minus between here, continuous everywhere. If I put one inside the other, it's going to be continuous everywhere. Okay? Those are my results of this section. And we will do one
last one?
One final example here. Yeah. Number 33. Again, integrals of continuity. One last integral problem. It has a small hitch to it. It's a piecewise defined function. Well, 33. F of x is the piecewise defined function x squared plus 3x on one part of its domain and 2x on the other part. If x is greater than greater than or equal to 1, it's that. If x is less than 1, it's that. So we carefully switched up the notation. Usually you have the lower parts of the function here, meaning the lower values for the domain above. They have switched them. We're supposed to show that f is not continuous at x equals 1. So for part of this problem, we are back to continuity at a point for one moment. Continuity at x equals 1 alone. Now I'm going to show you a small thing we didn't have to worry about before. Okay? The function we had before, when it was piecewise, it acted completely one way for every value of the function, for every function value of the domain, except for one value. This is different. This is one function that's going to coalesce into another one for the rest of the way, right? One half of your picture, in a sense, half of the picture is x squared plus 3x. The other half, in a sense, is 2x, okay? Whereas before, the picture was all one thing except for one point, right? So this is going to cause us to use left and right-hand limits for this problem, okay? I will show you why. So if we want to show it's not continuous at x equals 1, we start with the definition. We first try to find the limit of f of x as x approaches 1. We need to find that and make sure it exists, right? That's the first part of the definition of continuity at a point. So when we try to find this, the problem is it is acting one way to the left of 1, it is acting another way to the right of 1, right? It's not the same function on both sides because it's piecewise. And the pieces connect, in a sense, whether they actually connect directly or not is what we're trying to find out, at 1. So if this exists, that means we need to find, as x approaches 1 from the right, and we need to find the limit as x approaches 1 from the left. If these two things are the same, then this exists, and we can proceed further with the definition of continuity. Make any sense or not? Yeah? Okay. So basically, without drawing the full picture, can we draw the picture or not?
Can you just plug it?
Draw the picture?
I said, can you just plug it?
Okay. So first of all, which part of the function am I dealing with? X is approaching 1 from the right. Which part of that am I dealing with? Top. X is greater than or equal to 1. That's what I'm talking about here, right? X is greater than or equal to 1. They switched it on. That's what I'm trying to say. They switched the inequalities on you for whatever reason. I don't know why. So, what's that? Now you can plug it in. You gotta make sure you're using the right function though, right? Make sure you're writing the right notation. So you're trying to find the limit of x squared plus 3x as x approaches 1 from the right. So you're correct. Now it's a polynomial. You can just plug it right in, right?